Okay, good afternoon, everyone. Let's start then, okay? And once again, we are going to talk about derivatives of trigonometric functions. And from high school, again, you know what is the derivative of sine equals cosine, derivative of cosine equals negative sine, and tangent cosecant. And we are just going to review them one more time, okay? So what we are going to talk about here is simply how do we differentiate sine function, cosine function, tangent function, cotangent, secant, and the cosecant functions. Again, actually, to differentiate all of the functions, just we need to differentiate sine and cosine, and we know that we can derive other functions using these two functions, right? They are, what is it? Sine function and sine over cosine, that's equal to tangents, and cosine over sine, that's equal to cotangent, right? And 1 over sine, it is cosecant, 1 over cosine is secant function. But before I start this, you have already done this, I'm sure, that because in the book, this limit appears, but one more time, I would like to, what is it? What?
Nó xài mà phải nó trụ vật phải xài bình xài kho
Okay, one more time, I would like to evaluate this limit. Y, limit of cosine of h minus 1 over h when h approaches 0 is equal to 0. Okay, so now if you remember, we have studied the trigonometric identities in the first chapter, like cosine of, what is it? Let's say this h, right? I can write it as, what is it? Cosine of 2 times h over 2, right? So that means that now you can consider this h over 2 as alpha. So in two different ways I can write, right? Cosine of 2 alpha is equal to 2 cosine squared of alpha minus 1, or 1 minus 2 sine squared of alpha. So now I want to actually, what is it? Eliminate this one. That's why I need this form. 1 minus 2 times sine square root of alpha. What is our alpha? Here it is h over 2. Now, if you substitute here, then here we have cosine of h minus 1 becomes cosine of h is equal to 1 minus 2 times sine square root of h over 2 minus 1. And this 1 minus 1 is equal to 0. So here we have negative 2 times, and also this sine square root of h over 2, I can write it as sine of h over 2 times sine of h over 2. So now after this, if we evaluate our limits, the second one, what is this limit? This limit as h approaches 0. In the numerator, cosine of h minus 1, I can write minus 2 times sine h over 2 times sine h over 2. In the denominator, we have h. I can rewrite this. I can just bring this 2 down, right? And negative 1, I don't need negative 1. Anyway, let me just keep it there. Limits as h approaches 0. I can rewrite this as sine h over 2 times sine h over 2 over, and here we have h over 2. And here we have minus, right? This actually 2, it just actually comes here. So now we are familiar with all of these limits, right? When h approaches 0, right? And this approaches 0. And how about sine of theta over theta? Also, we have proved this. When actually theta approaches 0, this limit approaches 1, right? So that's why this limit is equal to minus 0 times 1, which is equal to 0, okay? Because I'm going to have this limit improving or deriving the formula for the derivative of sine and cosine. That's why first we have to know that it's equal to 0. So I don't have to calculate again and again, okay? So now let's start with it first. The derivative of the sine function is a cosine function. Why is it so? Okay, by using the definition, because without using any other method, we cannot obtain this. The only way to obtain this, we have to use the definition. And also for cosine, we have to use a definition. But other functions, by using the sine and cosine, we can obtain. That's why we don't have to use a definition to obtain the formula for example, the derivative of tangent function or secant function or cotangent function or tangent function. Now, again, we are just going to use the definition. What is the definition? The definition is f of x plus h minus f of x over h, right? Here our function is sine function. So the derivative of sine function x is equal to, that means that we have to evaluate this limit. Limit as h approaches 0, sine of x plus h minus sine of x over h. And also this sine of alpha plus beta in chapter 1 we studied, right? What is sine of alpha plus beta? That's equal to sine of alpha cosine of beta plus sine of beta cosine of alpha. So now if I just actually expand this sine of x plus h, I have here sine of x cosine of h. And plus, it must be plus. Let me correct this immediately, or otherwise it must be plus, right? Okay, so sine of x cosine of h plus sine of h cosine of h. Oh, there's sine of h. This one is x. Sorry. Okay, sine of x cosine of h plus sine of h cosine of x minus sine of x, right? So now, if I just again rearrange this, why? Because I have to rearrange in such a way that I will just bring this to the form that I know the limit. So now limits as h approach 0. Here, right, is sine of x, sine of x. Sine of x is a common factor. So I can rewrite here sine of x times inside parentheses, we have cosine of h minus 1 over h, I want to write here. And plus the second one is, here we have sine of h over h times cosine of x, right? So now we know how to evaluate these limits, because the sine of x, it's not dependent on h, so it's like a constant for h, function of h, right? So that's why its limit is equal to sine of x. And cosine of h minus 1 over h, as h approaches 0, we had just proved this, that's equal to 0. Plus, and sine of h over h, what, as h approaches 0, also we have proved this, that's equal to 1. Cosine of x is not dependent on h, that's equal to cosine of x. Now, if you just simplify this, that's equal to cosine of x. Okay, so now we can just take this as a fact. The derivative of sine function is equal to cosine function. Okay, next thing is, now let's see immediately a few examples involving the sine of x and the rules that we have already studied. Let me just use green here. What is the derivative of this function? Find the derivatives of these functions. Y prime is equal to derivative of x squared, that's equal to 2x, minus derivative of sine of x, that's equal to cosine of x. And how about here? We have the product of two functions, right? U times v. U function is x squared, v function is sine of x. So derivative of this function is equal to, if you differentiate x squared with respect to x, that is 2x, and u v function, that's equal to sine of x. Plus, now here we have x squared. What is the derivative of sine of x? That's equal to cosine of x. And the last one, we have the quotient, right? And what is the quotient of two functions? That's sine of x over x. So that's equal to y prime. And what is u over v prime? That is u prime v minus u v prime, right? If you differentiate sine function, that's equal to cosine of x times x minus, now I need to write sine of x times, what is the derivative of x? That's equal to 1 over, now we have to square this, right? Square this, that's equal to x squared. We just write this x the same. And now we can simplify this. If you just simplify that, what we have here, we have cosine of x, maybe I need to write x here, minus sine of x over, it is x squared. So that is the derivative of this function. And next thing is derivative of cosine function. Okay, the derivative of the cosine function is the negative of the sine function. And again, actually, we don't have any rule here, because as you know that cosine sine functions, they are transcendental functions. By just actually using the identity function f of x or a number 1, right, we cannot obtain this function. That's why the only way to prove this one is we need to use the definition. So now again, what is our definition? the derivative cosine of x, right, means that we need to evaluate this limit. If this limit exists, then we can claim that it has derivative or it is differentiable and its derivative is equal to this. So by definition, that's equal to cosine of x plus h minus cosine of x over h, right, limit h approaches 0. Right? And now again, what is cosine of alpha plus beta? If you remember, cosine of alpha plus beta equals cosine of alpha, cosine of beta minus sine of alpha, sine of beta. So here we have x plus h, our alpha is x and beta is h. Cosine of h, cosine x, cosine of h, right? Because the plus minus sine of, again, this must be x. Okay. So cosine of x, cosine of h minus sine of x, sine of h minus cosine of x. Now again, I'll just rearrange this. So here, these terms, right? What is the common term? The common term is cosine of x. So I'm going to factor out this cosine of x. Here we have limit as h approaches 0. The first part, the cosine of x is the common factor. So here we have cosine of h minus 1 over, here we have h. Minus the second part, here we have sine of x times sine of h over h, right? Actually, it's similar to the previous one. Now we know how to evaluate these limits. So the limit of this cosine function, that's equal to cosine of x because it's not dependent on h. And this limit we have just evaluated, that's equal to 0 minus, and here we have sine of x because the limit of this function is sine of x. It's not dependent on h, and limit of this function is a special one that's equal to 1. Now, if you simplify this, 0 times anything is 0 in real number system. So the result is sine of x. So now that's it about trigonometric functions. Others are just, what is this? The combinations of these two functions, right? We will see that a bit later. Okay, what is the derivative of tangent function, cotangent function, secant, and cosecant? That's it. We have actually only 6 trigonometric functions. So some examples related to this. The first one, what is the derivative of 5x plus cosine of x? Y prime is equal to, it is 5, plus cosine of x, it is minus sine of x. That's why, and it's just right here, minus sine of x. And how about here, sine x times cosine of x, right? The product of two functions. So the derivative of two functions is sine of x. That's equal to cosine of x times cosine of x, u prime v, that is cosine of x plus, and here we have sine of x, derivative of cosine of x, that's equal to minus sine of x. Now, if you simplify this, here we have cosine square root of x minus sine square root of x, right? And if you remember, what is this? Cosine square root of x minus sine square root of x, that's just equal to cosine of 2x, right? That's equal to cosine of 2x in a more compact form. And how about C? In C, y prime is equal to, again, here we have u over v, right? The quotient of two functions, that is u prime v minus u v prime. So our u is cosine of x. If you differentiate cosine of x, that is minus sine of x times the denominator, that's 1 minus sine of x. Minus, now I should just write here cosine of x. What is the derivative of minus 1 minus sine of x? Derivative of 1 is 0. And minus just add a coefficient, right? And sine of x is equal to cosine of x. So that is minus cosine of x over, in the denominator, we have 1 minus sine of x squared. And next step is just simple algebraic manipulation. We have to simplify. So if you simplify the denominator, numerator, minus sine of x times 1, that is minus sine of x. Minus minus, it is plus. Sine sine, it is sine square root of x. Minus minus, it is plus cosine square root of x. Over, that's equal, we have 1 minus sine of x squared. And we know that actually this sine squared of x plus cosine squared of x, that's our first identity we proved in our class, why that's equal to 1. Maybe that's the most popular one or the main famous one among the trigonometric identities. So in the numerator, then what we have here? Here we have 1 minus, right, is the sine of x. 1 minus sine of x over 1 minus sine of x squared. So now if you simplify this, finally we have 1 over 1 minus sine of x. So it's just equal to 1 over 1 minus sine of x. Okay. Simple harmonic motion. Okay, in math, actually, this harmonic, you'll see a lot in the future. I mean, if you, especially civil engineering students, you will see this, what is this, in calculus 2. You will see this in maybe in calculus 3. Also, you will see this, what is it, in differential equations. Usually, actually, this harmonic means that actually every in a step, the value of the number is getting smaller and smaller and smaller. By how? For example, 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. That is, for example, we call this harmonic series. And also here, the motion of an object or weight bobbing freely up and down with no resistance on the end of a spring is an example of simple harmonic motion. As you see in this video, right here, we have a kind of spring, and we just attach some kind of weight here, maybe a few grams of weight here because of its force, right? If we just actually leave it because of this force, actually just goes through this kind of, what is it, up and down motion. So the motion is periodic and repeats indefinitely. Indefinitely means that if you assume that there's no any external force acting on this body, right? At the time, it never stops. Yeah, just imagine that is a kind of ideal environment, maybe vacuum, right? There's no any external force acting on this. So we represented using trigonometric functions because trigonometric functions, that's maybe the most useful functions to describe, what is it, periodic motions. So the next example describes a case in which there are no opposing forces such as friction or buoyancy to show the motion. But I'm not asking you to learn in detail. You're going to learn this in physics class. Okay, we are just going to consider the mathematical part of this phenomenon. A weight hanging from a spring is stretched down 5 units beyond its rest position and released at time t equals 0 to bob up and down. Its position at any later time t is given by this equation, s equals 5 times cosine of t. Okay, so what's going on here? Actually, we are just attaching a kind of spring, and here we have a spring, right? And this one is that's initial position, right? And we have a weight here, and you're just pulling down somebody, let's say a Manet. I can see Manet here. It's just actually stretching this down, right? Down. And after that, just leave it. And after that, it starts bobbing up and down, up and down. So what is its velocity and acceleration at time? So we know that since this s, right, s of t is equal to 5 times cosine of t is our position function at any time t, it gives us the position of this particle, right? If you just draw, for example, it's just actually bobbing up, and this one is rest position, right? And on this interval, it's just bobbing up and down, right? At any time t, here, at any time t, for example, t, so position is here, right? So the question is, what is its velocity? In the previous section, we have studied that, what is it if you're given position function, if you differentiate this, its derivative gives us the velocity of the particle, right? If you differentiate this one more time, it gives us the acceleration. So to find the velocity function, Vt, and if we have to differentiate this, that's equal to minus 5 times sine of t. That is the velocity of this, harmonic, harmonic motion, this particle and weight. And how about this acceleration at time t? Acceleration is, if you differentiate this one more time, that's equal to minus 5 times cosine of t. That's it. You have to know this much for now. Okay, it's just given at different positions. T is equal to 0, and there's t is equal to, what is it, rest position, and t is equal, or position at t is equal to 0, and blah, blah, blah. At different positions, the graph is given. Anyway, that's not so important for us right now. The jerk of the simple harmonic motion in example 3 is, jerk is, we have to differentiate the acceleration, right? And acceleration is, we have just calculated that's equal to -5 times cosine of t. Now, if you differentiate this one more time, we get 5 times sine of t. So that means that it has its greatest magnitude when sine of t is equal to 1 or plus 1, right? Because when actually this one, right, is just coming to the lowest position, and here immediately it's changing in this direction. So that at this moment, there's a jerk, right? And moving up, right, at this position, again, it is just changing, making U-turn, right? But very quickly. So at these points, there's a jerk. So what is the jerk? That is 5 times sine of t. It has its greatest magnitude when sine of t equals plus minus 1, not at the extremes of the displacement, but at the rest position, where the acceleration changes direction and the sign. Okay. Some derivatives of the other basic trigonometric functions: tangent, secant, cosecant, and cotangent and cosecant. Now let's start with the first one. Actually, I hope from the first chapter, when we proved that, first we proved cosine of alpha minus beta, and using this one, we proved all other identities. In math, usually, you know, it is conceptual subject. Everything develops in this way. So we just actually give the definition. Using definition, we are just obtaining a few properties, and that means tools, and using properties or theorems, let's say tools, we can obtain all other functions. You can carry out all other functions. So now let's start with the first one. Why? The derivative tangent of x is equal to this. Let me just write it as a prime notation, tangent of x prime, right? So that's equal to, that is sine of x over cosine of x prime. And now we have just actually, you know, the rule how to differentiate the quotient of two functions, u over v. So that's equal to, I need to differentiate sine function. That's equal to cosine of x, and write the denominator, cosine of x minus, now write the denominator, sine of x times, now differentiate the denominator. That's equal to minus sine of x over, here we have cosine squared of x. Now, if you simplify the numerator, cosine squared of x minus minus is plus sine squared of x, which is equal to 1 over, here we have cosine squared of x. Now, actually, I can write this in a more simpler form than dot, 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 derivative of tangent x with respect to x, right here, tangent of x is equal to, what is it? 1 over cosine is second function. So that's equal to secant squared of x. Okay. And the second one is the cotangent. Again, what is the derivative cotangent function? Cotangent of x prime. In similar way, cotangent is defined, not defined, actually, identical is equal to cosine of x over sine of x. And here we have prime. And derivative of cosine, that's equal to minus sine of x. And here we have sine of x, right? Minus, and here we have cosine of x. Derivative of sine of x, that's equal to cosine of x. And over, here we have sine squared of x. So now if you simplify the numerator, again, as here, -1, right? It's a common factor, sine squared plus cosine squared, that's equal to 1. So here we have -1 over sine and squared of x. So now, again, we know that 1 over sine of x is defined as cosecant of x. That's why it's equal to minus cosecant squared of x. So the derivative cotangent function is equal to cosecant squared of x. Okay. In similar ways, secant and cosecant, you can actually obtain yourself. Like, for example, what is secant of x? Secant of x is 1 over cosine, right? Again, it's just the derivative of the quotient of two functions. It's constant function, 1 over cosine. So that's equal to derivative of secant is equal to secant of x times tangent of x. And derivative of cosecant of x, that is minus cosecant of x times cotangent of x. I'll just leave this as an exercise for you. Next example. What is the derivative of tangent function? Actually, I had just done this in a proof part, so I will skip this. Let me do maybe as an exercise. We can do, what's the next one? Okay, second function, right? So this one we have already done. This derivative of tangent function, right, is equal to what? That's equal to secant square root of x. Let's just do this one. So find y double prime. That means that the second order or second derivative of this function. Solution. First, what is y prime? That is secant of x prime. And what is secant? Secant is defined as 1 over cosine of x prime. And by using the quotient rule, right, derivative of 1 is equal to 0. 0 times cosine of x minus 1 times derivative of cosine, that's equal to minus sine of x. Over, here we have cosine square root of x. 0 times cosine of x, that's equal to 0. And negative 1, that's equal to 1. So here we have sine of x over cosine square root of x, right? Actually, we can just leave it like this, but usually in math is a kind of tradition that if you are performing some kind of operation on some function, okay, and the result of this operation also usually we try to, how to say, leave it in the form of the original function. Okay, that's actually, it really helps us to remember easily. So since we are talking about second function, right? So now, what is sine over cosine? That's equal to tangent, right? And now I can rewrite this one as, let me just write it. I can rewrite this as 1 over cosine of x times sine of x over cosine of x. Manipulation, algebraic manipulation. So what is the first part? 1 over cosine of x is defined as secant of x, right? And how about sine of cosine, sine over cosine? That is tangent of x. And that's why the derivative of secant x is secant of x times tangent of x. Now in the second part, actually we are asked here to find the second order derivative, right? So the second order derivative, that is y double prime, that means that I have to differentiate this function one more time, secant of x times tangent of x prime. And what is the derivative of second function? We have just put here, right? Actually, in the previous one, secant of x is equal to secant of x times tangent of x. Also here, so that is secant of x times tangent of x times the second function. The second function is tangent of x, right? Plus, now here we have secant of x. And what is the derivative of tangent of x? That's equal to secant square root of x. So now if you simplify this, let's see here, secant tangent of x, right? Not tangent of x, only secant of x, right? Secant of x. So secant of x is a common factor. And here we have tangent square root of x plus and secant square root of x, right? Okay, that's it. Maybe I can simplify further, okay? That's how we actually, how to say, differentiate these functions. Okay, a few examples, and after that, I will finish today's class. Is there a value of C? This example from exercise 3.5. Is there a value of C that will make f of x, this piecewise defined function, continuous at x equals 0? And give reasons for your answer. Okay. So if you remember, when our function can be continuous, right? That means that at this point, at x equals 0, we have this continuity here, right? So when actually it can be continuous, if the limit of this f of x, right, as x approaches 0, must be equal to c. If it is so, at that time it will be continuous. Otherwise, it cannot. So that's why let's actually evaluate the limit. What is the limit of this f when x approaches 0, right? So when x approaches 0, x is not equal to 0. Everywhere else, when x is not equal to 0, our function is defined as sine square root of 3x over an x squared, right? So now I can just rewrite this as, what is it, limit, and here we have as x approaches 0. Let me just write it as, here we have sine of 3x over, and here we have 3x and squared, okay? And this actual 9 appears here. So actually we didn't have 9. That's why I should multiply this by 9, right? So now if you evaluate this limit, what happens? We know that this as x approaches 0, sine of 3x and also 3x, they approach 0. And that's why we are familiar with this limit. That's equal to 1, right? And times 9, that's equal to 9. So actually, if how did we name this one? That means that this function has continuous extension to x equals 0, right? X equals 0 means that actually there's only one hole. By just adding one point, we can close that hole. By what number? Actually, this point, right? What point is it? That point is 0, 9. So the question is there a value of c that will make this function continuous at x sub 0? The first one, our answer is yes. And the second one is why? Because of this limit. And with what point, actually by adding what point we can make continuous, adding this point to the function's graph, we can actually make it continuous everywhere. Another example, 6. Okay, I think with this example, I will finish the class. Is there a value of b that will make g of x equals x plus b and cosine of x, right? G of x is defined as x plus b when x is negative, and is defined as cosine of x when x is non-negative. Continuous at x equals 0 and differentiable at x equals 0, and give you reasons for your answer. Okay, number one, let's answer the first part. So that means that continuous at x equals 0 means that does this function have continuous extension, right, at x equals 0? Now we have to answer this question. So that means that we have to evaluate the limit of this function. Limit when x approaches 0 from right, because at 2 different points is different, right? And limits when x approaches 0 from left, right? So now, first, when x approaches 0 from right, that means that now x is assuming only positive values, right? And when it is positive, our function is defined as cosine of x. So if you evaluate this function, right, cosine of x, this limit is equal to 1. And how about when actually x approaches 0 from left, when x is negative, is defined as x plus b. Is defined as x plus b. So when x approaches 0, this function approaches b, right? So that means that is there a value of b that will make this function continuous at this? The answer is yes. Now what is that? B is equal to 1. What b is equal to 1, then this function has a continuous extension at x equals 0. Otherwise, it doesn't have. Now question B, what is it? Is it differentiable at x equals 0, right? Is it differentiable at x equals 0? How do we know this? To do this one actually at 0, so we have to actually evaluate these two functions, right? When actually x is less than 0, when it is greater than or equal to 0, right? So we have to evaluate again these two, what is it? Definitions. Limit when h approaches 0 from right, and the second one is when h approaches 0 from left. Second one is limits when h approaches 0 from left. So we have to evaluate this thing. G actually at 0, right? So 0, that is 0 plus h minus g of 0. G of 0 over h. And also here we have g of 0 plus h minus g of 0. And we have to, here we have h. So we have to evaluate these limits. If they are equal to each other, that means that right-hand limit and left-hand limit, if they are equal to each other, then we say that limit exists. Because at a single point, right, I cannot actually evaluate using only a single expression here. So now if you evaluate the second one, so here we have limits as h approaches 0 from right. So now here we have g of h, right, as 0. And when h approaches 0 from right-hand side, that means that our input function is positive, right? When it is positive, our function is cosine of h. Here we have cosine of h. What is g of 0? At 0, again, that's equal to cosine of 0 over, and here we have h. And we have just evaluated this. Cosine of 0 is equal to 1, and cosine of h minus 1 over h, when h approaches 0, right, from right or from left, that's equal to what? That's equal to 0. At the beginning of this lesson, we have proved this because cosine of 0 is equal to 1. How about here? Here we have limits as h approaches 0 from left. So here we have g of h, right? Now it's approaching from left. When it approaches from left, that's equal, is given by x plus b, right? What is the value of x is equal to 0? So that's equal to b minus g of 0. That is cosine of 0. Cosine of 0 over h, right? And actually, when approach h, this cosine of 0 is equal to 1. And how about b? We know that b is equal to 1, right? b1 is equal to 0. So this limit is equal to 0, right? Because b is equal to, what is it? We have already found in the first part, b must be 1. So we are talking about at this point. At this point, the function is continuous if b is equal to 1. So if b is equal to 1, then at the point, the function is differentiable. The value of this thing is equal to 0. Okay, guys, we have one more question, but after this, you have quiz. So I'd like to stop here. I wish you good luck, guys. You have a link. You know how to do that. Once again, you need to enter your email address, okay? Section 1, Section 2, Section 3. Everybody use your own email. Like, if you make this kind of mistake, okay, just copy from somebody and use this. Section 1 student does, Section 2, for example. You know, it just caused some problem for me. It's not a big problem, so I just waste my some time. That's why I may deduct some points, at least 20 points, okay, from your quiz result. That's why open your Google Classroom and there's a link and just click on it. It opens at 3 o'clock. If there's any problem, immediately you can write in Telegram, okay? Thank you very much and good luck. Have a nice day. See you next week. Bye-bye.
Hello, sir. So will you drop the annotated slides to the classroom?
You mean this one?
Yes, yes.
Okay, okay. If you want, I will share. Or not actually Google Classroom because I have already put, not to confuse. I can drop this in Telegram, okay?
Yes, yes. Thank you, sir. Thank you.
Thank you. Thank you.